AP Chemistry, we're on to Lesson 5 in the Acid Bases unit, and this is the it's on acid-base interactions. So what we're going to do is look at how acids react in different with different bases, and in water and with some additional bases. We're going to go ahead and talk about strong acids and weak acids. Now, we've already done that. How do they react in water alone, if they're only in water? Then we're going to talk about how do strong acids react with strong bases, and how do strong acids react with weak bases. So that's kind of new. There's no problem solving here. It's really, this is a conceptual lesson so that you can kind of visually see how acids react in these different situations. So in the acid-base section, we dealt with acids reacting with water. We've done that in the last few lessons. So when the proton from hydrochloric acid, HCl, and we're kind of going to use that as our representative strong acid. Hydrochloric acid is a strong acid, one of the 7 strong acids. So when the proton from hydrochloric acid is dissociated, it leaves behind a chloride ion. The lone pair of a water molecule can attract a hydronium ion, H+, or H3O+, making it a base. So what remains behind is a negatively charged chloride ion. The proton, in the absence of any other substances, attaches to the lone pair of a water molecule to become H3O+, the hydronium ion. And that'll happen 100% of the time. As many hydrochloric acid molecules as you put into an aqueous solution, that many will donate their proton to a water molecule. So a base that differs from an acid, just a reminder of this definition, a base that differs from its acid by exactly 1 proton is called a conjugate base. So chloride and hydrochloric acid are conjugate acid-base pairs. Just an additional note, I kind of call chloride a fake base. It's a fake base. It's not really a base. A chloride ion, a Cl-, will never accept a proton from anything. Protons will not come and associate and jump onto a chloride ion. Okay, it only not in water. It only happens outside of water where that covalent bond can take place. Okay, so let's start with the first one, strong acid. So strong acids have complete dissociation of H2O, producing H3O+. So every strong acid molecule will turn into a hydronium ion. For that reason, if you see the molar concentration of a strong acid, such as hydrochloric acid, you know that in water it's going to produce that exact same molar of hydronium ions. So 2.4 molar of HCl in water will produce 2.4 molar of hydronium H3O+ ions. Okay, so strong acids completely dissociate in water. This means that every strong acid molecule that enters water will give a proton to a water molecule. So there we see hydrochloric acid. Again, the blue area is just entirely water molecules. We're just showing one right here on the right just to represent one of the water molecules in that beaker of water. So the strong acids completely dissociate in water. This means that every strong acid molecule will give a proton to a water molecule. So there it goes. So the chloride ion, Cl- is the conjugate base of hydrochloric acid. The conjugate base of a strong acid never accepts a proton, what I was saying earlier. So it will never take back that proton. It will just remain in solution as Cl-. There are a few elements we talked about in solubility rules that it will bond with, but it will not take back a proton. So chloride is neutral. It does not change the pH of the solution. The water molecule becomes a hydronium ion, H3O+. Here, water acted as a base by accepting a proton. H3O+ lowers the pH. It makes the solution more acidic and therefore makes the pH go down. Now let's look at weak acids, and we've talked about this. So some, usually very small dissociation of hydronium to H2O of protons to H2O to produce hydronium ions. Again, H+, H3O+ are the same thing. because they will all go immediately to a water molecule. Now, it's with weak acids that we need to use Rice tables and law of mass action, what we've been doing for the last few lessons. Don't need to use those for strong acids, but you do need to for weak acids. So hydrofluoric acid, you see that over there on the left. You see 4 molecules of hydrofluoric acid, HF. Although it looks like HCl, the way it's visually diagrammed there, it is not a strong acid like HCl. It is a weak acid. It's not one of the 7 strong acids. So when we put HF, hydrofluoric acid, in water, only a small fraction of the molecules will dissociate and pass their protons to the water molecule. So we're just going to use a representative sample here. If we put 4 hydrofluoric ions in water, HF does not completely dissociate. This is the definition of a weak acid. In this example, we will say that 1 out of 4 hydrofluoric molecules ionizes and passes a proton to water. The actual number for hydrofluoric acid is really about 1 out of 10,000 will do it. So there goes one of them over there. And we put X's in front of the others, meaning they're not going to dissociate. Now remember, in a dynamic equilibrium, that proton that was just donated to the water can go back to that hydrofluoric acid, and then a different hydrofluoric acid can donate a proton, and then it can go back. It's just simply on average, in this example, 1 out of every 4 at any one time is ionized. So remember that dynamic equilibrium means that the ionized hydrofluoric acid can take back a proton, and any of the other hydrofluoric acids can pass a proton to the water molecule. So the fluoride ion F- that remains is a conjugate base of hydrofluoric acid. The proton can return to that fluoride ion. So the fluoride ion actually is a base. It can take back a proton. Unlike chloride, the chloride Cl-, the fluoride actually can take back a proton. That's true of any weak acid that has dissociated. So it's true of the conjugate base of any weak acid. It can take back a proton. Weak acid problems require a Rice table and law of mass action to compute the concentrations. That's what we've been doing in the last couple of lessons. Now we're going to move on to something that we haven't talked about. And that is, what if we have both a strong acid and a strong base in solution? And in this example, we're going to say that there's more of the strong base than there's more of the strong acid than the strong base. That's what's meant by excess strong acid with strong base. It means if you put them together, you're going to run out of the strong base first, okay? And then you're still going to have some of the acid left in the solution. So complete dissociation of the H+ to completely dissociated OH- base until neutralized, then to H2O producing H3O+. So let's get into it and let's see what that means. So here we have, let's look at what we have here to start. We have in the water a water molecule that we're going to react with. And then up above on the right side, you have a sodium hydroxide, NaOH. That is a strong base. That Na, if you look at your solubility rules, will break off of that hydroxide 100% of the time. It's completely soluble. Over on the left, we have 2 hydrochloric acid molecules. So let's see how they react with each other. So in the acid-base section, we dealt with acids reacting with water. It is possible for an acid to react with a base other than water. So there you have sodium hydroxide. It's a strong base. It completely dissociated into Na and OH-. So we're going to see that in a minute. So there goes the sodium, and we're just going to set it off to the side. It's a spectator ion. It doesn't play any further role in this reaction. So there it is sitting on the bottom, and we're going to change it into an Na+, okay? It left its electron behind on the hydroxide, and so now you look at the hydroxide up there, OH, it's OH- because it has that extra electron left behind by the sodium. Na is a spectator ion. It has no effect on the reaction. OH- becomes a negatively charged cation. So now it has a charge to attract a proton. A strong acid such as hydrochloric acid is added to the solution. Since it is a strong acid, we know it will completely dissociate. HCl will completely dissociate to both hydroxide ions, OH-, and water molecules. So here it goes. It's now going to go into the solution. So which of the two molecules would HCl rather pass the proton to? The hydroxide or the water molecule? We know it will totally dissociate with the water molecule, but now there's also a hydroxide, OH-. Which one would it prefer to pass the proton to? So hydroxide, OH- has a stronger negative charge than H2O because, let's say because before we go to therefore, it's because hydroxide has a full 1- charge. It has an extra electron. That's a 1- charge, so that's a pretty strong negative charge. Remember that water is electrically neutral, but it's a dipole. It has a negative side, which is the oxygen side, and it has a positive side, which is the hydrogen side. So you have a full 1- charge in hydroxide versus a partial negative charge on one side of the water molecule. So therefore, HCl or any acid will neutralize the OH ions to produce water. So the first one is going to want to go to the hydroxide because it has a stronger negative charge. 2, HCl or any acid will dissociate to the H2O to produce H3O plus hydronium ions. So its first choice is the hydroxide ion. Its second choice is the water molecule. So therefore, the proton will be attracted to the hydroxide over the water molecule, at least the first one. So when the H+ attaches to the OH-, it forms a water molecule. Water is a neutral substance. It has a pH of 7. That's right in the middle of the pH scale. So this is called a neutralization reaction. When an acid and a base, in this case a strong acid, hydrochloric acid, and a strong base, sodium hydroxide, when they get together, they will neutralize. So let's watch this happen. Acids and bases can neutralize each other so that the solution is neither acidic nor basic. So we're going to move that water molecule, and here goes the proton. So what you did is you had an acid molecule that had not dissociated yet. So the hydrochloric acid was not yet producing H3O at that point. In fact, it still isn't. However, the hydroxide was causing the solution to be basic, to have a base pH, to be moving upward. Now when that proton got passed from the hydrochloric acid over to the hydroxide, look what you have. You have a chloride ion there. We're only talking about the molecules on top now. You have a chloride ion, which does not change the pH. And you have a water molecule, which does not change the pH. So it's still a neutral solution at this point. So after all hydroxide ions have been neutralized to become water, the remaining hydrochloric acid molecules will pass a proton to a water molecule, creating hydronium ions. So there it gets passed over. So its first choice is the hydroxide. That's a neutralization reaction. It produces Cl- and H2O, a water molecule. So that's a neutral, still a neutral solution. Now the second hydrochloric acid, there were no more hydroxide ions for it, so it decided, and we know it's going to 100% of the time pass its proton over to a water molecule to create a hydronium ion. So therefore we now have an acidic solution. Okay, so at the beginning, after the sodium hydroxide had dissociated, we had hydroxide. We had a basic solution, a base solution. Now, after both of these dissociations of the hydrochloric acid have taken place, we now have an acidic solution because we have a hydronium H3O ion in the solution now. So the H3O ions lower the pH of the solution towards the acidic range. The chloride ions Cl- are neutral and do not affect the pH of the solution. Don't get the fact that chloride ions are negatively charged with being acidic or basic. Negatively charged ion is not necessarily an acid or a base. It can be, but in this case, in the case of chloride, it's not. Chloride is neutral and does not affect the pH. So the chloride ion Cl- is not acidic or basic. It is neutral. The water molecule is also neutral. The one thing that contributes to the pH is that hydronium ion on the bottom right, and that is going to move the pH down towards the acid range. After all acid and base molecules have neutralized, the excess acid HCl will react with water molecules to produce hydronium ions. So any more HCl molecules we throw into that solution are going to totally dissociate. The proton's going to go to the water molecules that are in that solution. The creation of H3O plus means the solution becomes more acidic. So after the base OH minus has all been consumed, used up by taking protons from hydrochloric acid, the remaining acid molecules, HCl, will react with the water to form hydronium ions, H3O plus. Okay, now we're going to move on to excess strong acid and weak base. So that means that we're going to put acid in with base. This time it's a weak base, and the weak base is going to be consumed first. It's going to be used up first. If you want to use the word limiting reactant, the weak base would be the limiting reactant here. So excess strong acid with weak base. So the complete dissociation of H plus to the weak base and then to H2O to produce hydronium ions. So the weak base pretty much acts the same way as the strong base if it's in with a strong acid. Okay, so water is a weak base in the presence of an acid. It always acts as a weak base in the presence of an acid. When another weak base is present, it has a greater attraction for the proton H plus of an acid than water does. So the weak base has a pH greater than 7. So in this example, the NH3 is called ammonia, and that is a weak base. So in this example, in the example below, the strong acid HCl first dissociates to the weak base ammonia to form the ammonium ion. So that's really the question we're answering here. If you have both a weak base and a water molecule, which would the proton from the hydrochloric acid prefer to go to first? Does it want to go to the ammonia or does it want to go to the water? And the answer is it wants to go to the ammonia first, to that weak base, before it goes to the water. After all ammonia has been consumed, the strong acid dissociates to the H2O. That means the next proton is going to go to the water molecule because there's no more NH3 left, and that's going to create hydronium ions, and that makes the solution acidic. Presence of hydronium ions is what makes the solution acidic. So there goes the first proton. It wants to go to the ammonia, not to the water molecule. It therefore creates NH4 plus, that's the ammonium ion, and that's the conjugate acid of ammonia. Ammonia is a base, NH3, ammonium, NH4 plus, is the conjugate acid of the base ammonia. So the strong acid first neutralizes the weak base, NH3 plus, creating NH4 plus. So now you have a weak acid in solution, a weak conjugate acid in solution. Then the second proton will then go ahead and completely 100% of the time, because it's a strong acid, dissociate to the water molecule to create the hydronium ion, H3O plus. So any remaining hydrochloric acid will dissociate to H2O, creating an acidic H3O plus solution. The H3O plus will lower the pH toward the acidic range. Okay, and finally, down at the bottom, it says weak acid and weak base. This is not discussed. It's never discussed in a first-year chemistry course. It's not in your textbook. I have never done a problem with a weak acid, weak base, but I'm told they're complicated, and they're beyond the scope of any first-year college chemistry course. So you would never be asked that in any first-year college chemistry course or on the AP exam. So we just ignore weak acid, weak base put together in a water aqueous solution. All right, and that takes care of this lesson. It's a conceptual lesson, but you want to know how a strong acid is going to react with each of the different kind of situations it could be in. A strong and a weak acid. Is it just in water? Is it in the presence of a weak base, or it is in the presence of a strong base? And that's what we've talked about today. So that takes care of this lesson.